SwayamPrabha. Digital India. Educated India.
Hello and welcome back. Today we will be discussing few problems related to exergy. So in the first question, a house that is losing heat at a rate of 50,000 kilojoule per hour when the outside temperature drops to 4 degrees Celsius is to be heated by electric resistance heaters. If the house is to be maintained at 25 degrees Celsius at all the times, determine the reversible work input for this process and the irreversibility. So this diagram shows the house which is maintained at 25 degrees Celsius and it is losing heat at a rate of 50,000 kilojoule per hour, and the surroundings or the outside temperature is maintained at 4 degrees Celsius. Now it is heated using an electric resistance heater. So the actual power input is W in dot, which is also equal to the rate of energy which is going out, and it is equal to QH dot, and this is 50,000 kilojoule per hour, or it can be written as 13.89 kilowatt. Now if we draw a heat pump, so it is like heat pump which is used to maintain a temperature of 25 degrees Celsius, and this is QH dot, which is equal to 50,000 kilojoule per hour, and some work is being given as input, and the outside temperature is 4 degrees Celsius, and this is QL dot. Now because the power which is lost by a house is continuously supplied by resistance heater to maintain a constant temperature, so the COP of this heat pump will be for a reversible process is TH, which is 25 degrees Celsius, divided by TH minus TL, and TL is 4 degrees Celsius. So this becomes equal to 298. So this is equal to 14.2. Thus the reversible work input is QH dot divided by COP of the heat pump. So this is coming from the definition of COP. So COP is QH dot divided by W reversible in dot. So QH dot is 13.89 divided by COP, which is 14.2. So reversible work input is 0.978 kilowatt, and we also need to determine irreversibility. So irreversibility is I dot is equal to actual work input minus the reversible work input. So this is equal to 13.89 minus 0.978, this is equal to 12.91 kilowatt. So this is the irreversibility of this process. Moving on to the next question. In this question, consider a thermal energy reservoir at 1500 Kelvin that can supply heat at a rate of 150,000 kilojoule per hour. Determine the exergy of this supplied energy assuming the environmental temperature at 25 degrees Celsius. So for this, if we take it as a heat engine, so it takes energy from a reservoir which is at 1500 Kelvin, and it is supplying heat at a rate of 150,000 kilojoule per hour, and the environmental temperature is 25 degrees Celsius and some work is being produced. So we have to calculate the exergy of this supplied energy. Now the thermal efficiency of this heat engine is, for a reversible process, is 1 minus T0 by Th. So T0 is the environmental temperature and Th is the temperature of the reservoir. So this is equal to 1 minus 298 divided by 1500. So this is equal to 0.8013. Now the exergy of the supplied heat in the rate form is the amount of power that will be produced by a reversible heat engine. So exergy is equal to maximum work out, or it is also equal to the reversible work which comes as output, and this can be written in form of efficiency, maximum efficiency multiplied by the heat which is given as input. So this is equal to 0.8013 multiplied by Q in, which is 150,000 kilojoule per hour. So this is equal to 0.8013 multiplied by, converting R into second, so it will be 3600 kilojoule per second, and this comes out to be 33.4 kilowatt. So this is the exergy of the supplied energy. Now in the next question, which has the capability to produce most work in a closed system? 1 kg of steam at 800 kilopascal and 180 degrees Celsius, or 1 kg of R134A refrigerant at 800 kilopascal and 180 degrees Celsius. The surroundings are at 25 degrees Celsius and the pressure is 100 kilopascal. So we have to compare which has the more capability, 1 kg of steam or 1 kg of refrigerant at the same conditions. So first, taking steam into consideration. So for steam, the conditions are 800 kilopascal and 180 degrees Celsius. So if we see from table A6, at this we will find in the table the values are given for 170.41 degrees Celsius and 200 degrees Celsius. Now to calculate the values, we need to interpolate between these two temperatures to get the values at 180 degrees Celsius. So after interpolation, we get the values as U is 2594.7, specific volume is 0.24720 and entropy as 6.7155. For the environmental conditions, it is at 25 degrees Celsius and 100 kilopascal. We can directly obtain these values from the table A4 at 25 degrees Celsius, and these are the properties of saturated liquid. Now the exergy of this steam is a measure of the work potential. So if we calculate exergy, of steam, so this is equal to m u minus u0 plus P naught, which is the pressure of the surrounding, into V minus V naught minus T0 S minus S0. Now putting all the values, mass is 1 kg, U is 2594.7 minus U0 is 104.83 plus pressure is 100 kilopascal, V minus V0 is 0.24720 minus 0.001003 meter cube per kg, and converting the units and making all the units consistent. So 1 kilojoule is equal to 1 kilopascal meter cube. So this will make the units consistent, minus T0, which is 298 Kelvin. multiplied by S minus S0, so S is 6.7155 minus S0, which is 0.3672, and this is kilojoule per kg Kelvin. So this gives a value of phi, which is equal to 622.7 kilojoule. So this is the capability of the steam to produce work. So this much work can be produced by the steam. Now moving on to the refrigerant R134A. So at the given conditions 800 kilopascal and 180 degree Celsius, the values from the table A13 are U is this, V specific volume is this, and entropy is this. Now for the environmental conditions, that is 25 degree Celsius and 100 kilopascal, it is again superheated. So we need to see the values. So at T0 is equal to 25 degree Celsius and P0 is equal to 100 kilopascal. These values are U0 is equal to 252.615 kilojoule per kg, V0 is equal to 0.23803 meter cube per kg, and S0 is equal to 1.10605 kilojoule per kg Kelvin. Now these values are obtained by interpolating between 20 and 30 degrees Celsius, because directly the values are not given in the table A13. Similar procedure is followed as done for steam. So phi exergy is given as m U minus U0 plus P0 V minus V0 minus T0 S minus S0. Putting all the values, so mass is 1 kg, U is 386.99 minus U0 is 252.615 kilojoule per kg plus P0 is 100 kilopascal. Multiplying this by V minus V0, so V is 0.044554 minus V0 is 0.23803, and it is meter cube per kg. Again 1 kilojoule is equal to 1 kilopascal meter cube minus T0, which is 298 Kelvin, to S 1.3327 minus S0, which is 1.10605 kilojoule per kg Kelvin. This gives a value of phi, which is equal to 47.4843 kilojoule. So if we compare the two values for the steam, the value is, so phi steam is equal to 622.7 kilojoule, and this for refrigerant, that is R134A, this value is 47.4843. So for steam the exergy is more, so it has the more potential to do work, or it has a more capability to produce work. Moving on to the next question. In this question, steam enters a turbine at 9 megapascal. This is a turbine. Steam enters at 9 megapascal, 600 degrees Celsius and 60 meter per second, and leaves at 20 kilopascal, 130 meter per second with a moisture content of 5%. So this 5% means X is 0.95. The turbine is now not adequately insulated, so some amount of heat is going out as it is not properly insulated, and it is estimated that heat is lost from the turbine at a rate of, so this is the heat loss from the turbine, so Q dot is 220 kilowatt. The power output of the turbine is, so this is the work produced by the turbine, 4.5 megawatt. Assuming the surroundings to be at 25 degrees Celsius, so outside is at 25 degrees Celsius, determine the reversible power output of the turbine. So there are various quantities we need to find. Second is the exergy destroyed within the turbine, second law efficiency, and also the possible increase in the power output of the turbine if the turbine were perfectly insulated. So moving step by step, if we find the properties of the steam at the inlet and exit state, so at 9 megapascal and 600 degrees Celsius from the steam table, at 600 degrees Celsius, as this is a superheated steam, so from superheated water table at 600 degrees Celsius, we know specific volume, internal energy, enthalpy and entropy. So H1 is equal to, this is taken as 0.1, this is taken as 0.2. So H1 is equal to 3634.1 from this table, kilojoule per kg. S1 is equal to 6.9605 kilojoule per kg Kelvin. Now for water, it is already given in the question that is a mixture of liquid and vapor. So we can find H2 from HF at 20 kilopascal, because the pressure is 20 kilopascal, plus X, which is 0.95 multiplied by HFG at 20 kilopascal. Now we need, for obtaining these values, we need to see the table of saturated water. So at 20 kilopascal, we can find that HF is 251.42, HFG is 2357.5, and also entropy SF is 0.8320 and SFG is 7.0752. So putting these values to obtain H2, so H2 is equal to 251.42 plus 0.95 multiplied by 2357.5, and this gives H2 is equal to 2491.045 kilojoule per kg. Similarly, S2 is obtained, which is equal to SF at 20 kilopascal plus X multiplied by SFG at 20 kilopascal. So this is equal to 0.832 as shown earlier in the table of saturated water vapor. So S2 comes out to be 7.5535 kilojoule per kg Kelvin. Calculating the enthalpy at the dead state, so T0 is equal to 25 degrees Celsius and X is equal to 0. So from table, H0 is equal to 104.83 kilojoule per kg, and this is equal to HF. So this value is HF at 25 degree Celsius. The mass flow rate of steam can be determined from energy balance on turbine. So energy balance on turbine will be E in dot minus E out dot is equal to delta E of the system. So delta E of system is 0 for steady flow process. Now energy in is the energy of this steam which is entering the turbine, so that is equal to mass times H1 enthalpy plus, because of the velocity with which it is entering, so it is the kinetic energy contribution, and this is equal to E out. So E out is mass, because mass entering is equal to mass leaving, so m dot 2 multiplied by H2 plus V2 square by 2 plus there is some heat loss plus some work is produced by the turbine. So putting all the values, H1 is 3634.1 kilojoule per kg plus the velocity at the inlet is 60 meter per second. Converting the units, this is equal to m dot. So H2 is 2491.045 1 kilojoule per kg plus 130 meter per second, which is the velocity at the exit, divided by 2. Now 1 kilojoule per kg is equal to 1000 meter square per second square. Also 220 kilowatt of heat is being lost by the turbine because of imperfect insulation, and also 4500 kilowatt of work is produced by the turbine. So this equation gives a value of m dot, which is the mass flow rate of steam, that is 4.137 kilojoule per second. For calculating the reversible power output, we can apply an exergy balance on the system and its immediate surrounding, and setting the exergy destruction term equal to 0. So xn dot minus x out dot minus x dot destroyed is equal to dx of system divided by dt. So this is 0 for a steady flow system, and this is also made 0 to obtain the reversible work output. So from this we get xn dot is equal to x out dot. This can be written as mass flow rate time, and this is equal to reversible work output plus. So from here reversible work output is m dot psi 1 minus psi 2. So this is equal to h1 minus h2 minus t0 s1 minus s2 plus v1 square minus v2 square by 2. Putting all the values, so m is 2.693, h1 is 3634.1 minus 2491.1 minus T0, which is 298 Kelvin, multiplying this by S1 minus S2. So S1 is 6.9605 minus S2 is 7.5535 plus meter per second divided by 130 meter per second, the out velocity at the exit. So multiplying this by 1 kilojoule per kg for converting the units, which is equal to 1000 meter square per second square. So this gives a reversible work output of 5451 kilowatt. Now the second part is we have to calculate the exergy destroyed within the turbine. So the exergy destroyed is that is x destroyed is equal to reversible work minus the actual work. So this is reversible work is 5451 minus the actual work produced is 4500. So this is equal to 951 kilowatt. The next part is to calculate the second law efficiency of the turbine. So second law efficiency is actual work divided by the reversible work. So this is equal to 4500 kilowatt divided by the reversible work, that is 5451 kilowatt. So it comes out to be 0.826. In the next part we have to calculate the possible increase in the power output of the turbine if the turbine were perfectly insulated. So to calculate the increase in the power, we know the energy of the steam at the turbine inlet at the given dead state is, so energy of the steam at the turbine inlet for a given dead state is Q dot, which is equal to m mass flow rate multiplied by H1 minus H naught. So, we know mass flow rate, which is 4.137 kg per second, and H1 is 3634.1 minus 104.83 kilojoule per kg. Now, so this is equal to 14602 kilowatt. So, the fraction of energy at the turbine inlet that is converted to power is F is equal to actual work divided by the energy of the steam. So, this is equal to 14500 divided by 14602. So, this is the fraction of energy which is converted to power. Now, if we assume that the same fraction of heat loss from the turbine could have been converted to work, the possible increase in the power would be, if the turbine is well insulated, so increase will be this fraction multiplied by the Q out dot, which is equal to 0.3082 into 220. So, a fraction of this which is wasted would have been converted into a useful work. So, these many kilowatts could have been converted into useful work. In the next question, an insulated piston cylinder device contains 0.8 liter of saturated liquid water at a constant pressure of 120 kilopascal. So, this pressure is maintained. An electric resistance heater, so this is the heater, inside the cylinder is turned on and the electrical work is done on the water in the amount of, so this is the amount of work done by this resistance heater. Assuming the surroundings to be at 25 degrees Celsius, so surroundings are at 25 degrees Celsius and 100 kilopascal. Determine the minimum work with which this process could be accomplished and the exergy destroyed during the process. So, if we find the properties at the given state inside the piston cylinder device or in the surrounding. So, for both from the table, saturated water pressure table at 120 kilopascal. So, we find that the values are not given at 120 kilopascal, rather we need to calculate the values at 120 kilopascal by interpolating between 101325 and these values and at a pressure of 125 kilopascal. So, after interpolating we get the values at 120 kilopascal. So, as this is mentioned that this is a saturated liquid, so all the values are obtained. U1, which is obtained by interpolating between these two values for 120 kilopascal. Similarly, V1 is obtained by interpolating between these two values to obtain the value at 120 kilopascal. Similarly, H1 is obtained from these two values and S1 from these two values. Similarly, all the other properties like HFG, SFG can be calculated by interpolating if required. So, the mass of the water in this device will be mass is equal to total volume, which is 0.8 liter divided by the specific volume. So, this is equal to 0.008 meter cube divided by specific volume, which is 0.001047 meter cube per kg. So, the mass of the liquid is 7.639 kg. Now, we take the contents of the cylinder as the system. So, contents of the cylinder as taken as a system. So, this is a closed system. Since no mass enters and leaves, so energy balance for this stationary system will be E in minus E out is equal to delta E of the system. Now, this can be written as WE in minus, this is the work when the system is heated because of this resistance heater. So, some work is done because this piston is being pushed up, and this is the electrical work which is given as input. This is equal to delta U, change in internal energy of the system. Now, we can write delta U plus WB is equal to delta H. So, this is the change in enthalpy of the system during a constant pressure quasi equilibrium process. From this, it is written as M H2 minus H1. So, from here, so this is delta H. So, this is the M H2 minus H1. So, from here we can calculate H2 is equal to H1 plus electrical work given as input divided by mass. Now, we know all the values. We can put H1 is 439.36 plus electrical work input is 1400, mass is 7.639. So, this comes out to be 622.63 kilojoule per kg. So, now we know the enthalpy at state 2. It is also known the pressure at state 2 is 120 kilopascal and H2 is 622.63 kilojoule per kg. So, from here we can calculate X2. So, X2 is equal to H2 minus HF divided by HFG. From the value of HFG at 120 kilopascal from the previous table, from this table by interpolation, we can get the value of X2. So, this is equal to 622.63 minus 439.36 divided by 2243.7, and it is equal to 0.08168. Similarly, the value of S2 is equal to SF at 120 kilopascal plus X2 multiplied by SFG. So, this is equal to 1.3609, 0.08168 multiplied by SFG, which is 5.93687. So, this gives S2 is equal to 1.8459 kilojoule per kg Kelvin. Similarly, U2 is equal to UF. So, I am directly writing the values plus X into UFG, which is 2072.4. So, this is equal to 608.52 kilojoule per kg, and V2 is equal to Vf, which is 0.001047 plus 0.08168. This is X2 multiplied by Vfg. This is equal to 1.4285 minus 0.001047, and this value comes out to be 0.1176 meter cube per kg. Now, we know the different properties at the exit state. The reversible work input, which represents the minimum work input, in this case can be determined from the exergy balance by setting exergy destruction equal to 0. So, applying exergy balance, which is X in minus X out minus X destroyed is equal to delta X of the system. Exergy destroyed is set to 0. So, from here we get work reversible input is equal to X2 minus X1. X1 represents the initial state and X2 represents the final state. So, work reversible input is equal to minus M U1 minus U2 minus T0 S1 minus S2 plus P0 V1 minus V2. So this is equal to minus 7.639 kg multiplied by U1 minus U2, which is 439.27 minus 608.52 kilojoule per kg minus 298 Kelvin, which is T naught, minus S2 minus S1, which is 1.3609 minus 1.8459 kilojoule per kg Kelvin, plus P naught V1 minus V2, so which is equal to 100 kilopascal multiplied by 0.001047 minus 0.1176 meter cube per kg, and making the units consistent. So 1 kilojoule is equal to 1 kilopascal meter cube. So this gives a value of reversible work input as 278 kilojoule. Now the second part is we have to calculate the exergy destroyed during this process. So B is exergy destruction. So exergy destruction can be determined from its definition as exergy destroyed is equal to T0 into S gen, where the entropy generation is determined from this term is determined from the entropy balance on the cylinder, which is an insulated closed system. So applying entropy balance, S in minus S out plus S gen is equal to change in entropy of this system. From here these two will be 0, so we get S gen is equal to delta S of system, and this is equal to M S2 minus S1. Now substituting X destroyed is equal to T naught S gen, so this is equal to M T naught S2 minus S1, and putting all the values, M is 7.639 kg, T naught is 298 Kelvin, S2 is 1.8459 and S1 is 1.3609, that is kilojoule per kg Kelvin. So this value comes out to be 1104 kilojoule. So exergy destroyed is 1104 kilojoule. Moving on to the next question, where a liquid water at 200 kilopascal, so this is a liquid water at 200 kilopascal and 15 degrees Celsius, so temperature is 15 degrees Celsius, is heated in a chamber by mixing it. So this is a mixing chamber, so this water is heated in this, mixing it with a superheated steam. So this is a superheated steam at 200 kilopascal and 200 degrees Celsius. Liquid water enters the mixing chamber at a rate of 4 kg per second. So this is the mass flow rate, and the chamber is estimated to lose heat to the surrounding air at 25 degrees Celsius. So surroundings are at 25 degrees Celsius and this heat is lost to the surrounding at this rate. If the mixture leaves the mixing chamber at 200 kilopascal, so this final mixture comes out at 200 kilopascal and 80 degrees Celsius. Determine the mass flow rate of the superheated steam. So this is the superheated steam, so for this we have to determine the mass flow rate and the wasted work potential during this mixing process. So for the first stream, if we see from the table, this is a compressed liquid. So we can approximate this compressed liquid from the properties of the liquid at its temperature, that is 15 degrees Celsius. So enthalpy would be at state 1, H1 is properties HF at 15 degrees Celsius, which is 62.98. The entropy would be the value SF at 15 degrees Celsius, which is 0.22447. Now for this state 2, it is at 200 kilopascal and 200 degrees Celsius, it is in superheated state. So, from the superheated table at these conditions, the H2 is 2870.4 and S2 is 7.5081, while the stream which is leaving is at 200 kilopascal and 80 degrees Celsius, it is again compressed liquid. So, the properties are estimated from those of the saturated liquid at the corresponding temperature, which is 80 degrees Celsius. So, H3 is HF at 80 degrees Celsius, which is 335.02, and entropy is entropy of the liquid at 80 degrees Celsius, which is 1.0756. Now, taking this mixing chamber as the system, the mass and energy balance can be applied. So, if we apply mass balance in the rate form, so mass which is entering minus mass which is going out is equal to change in mass of the system. So, this is a steady flow system. So, this is equal to 0. So, it gives m in dot is equal to m out dot. So, from here m mass entering is this stream 1 is entering and this 2 is entering. So, m1 dot plus m2 dot is equal to m3 dot. Now, applying energy balance on this mixing chamber, in the rate form. So, E in dot minus E out dot is equal to rate of change of energy of the system. So, again this rate of change of energy is 0 because of steady flow system. E in is equal to E out. So, this gives m1 dot h1, which is the enthalpy of stream 1, plus m2 dot h2, which is the enthalpy of stream 2. So, these two are entering. So, this is equal to E in, and the E out is equal to heat which is being wasted or lost to the surrounding, plus enthalpy of the stream which is coming out, that is m3 dot h3. Now, combining these above two relation of mass and energy balance. So, from here we can get Q out dot is equal to m1 dot h1 plus m2 dot h2 minus m1 dot plus m2 dot h3. So, this is equal to m1 dot h1 minus h3 plus m2 dot h2 minus h3. From here solving for m2, so we will get m2 is equal to Q out dot minus m1 dot h1 minus h3 divided by h2 minus h3. So, putting all the values, Q out is 600 by 60 kilojoule per second minus mass flow rate which is for m1 dot which is 4 kg per second, multiplying this by 62.98 minus 335.02. So, this is in kilojoule per kg, dividing the entire expression by H2 minus H3, which is 2870.4 minus 335.02, and this is in kilojoule per kg. So, this gives a value of m2 dot which is equal to 0.429 kg per second. So, this is the mass flow rate of the superheated stream which is entering. From this we can also determine the final mass which is coming out of the mixing chamber, that is m3 dot which is equal to m1 plus m2 dot, and this is equal to 4 plus 0.429, which is comes out to be 4.429 kg per second. Now, in the second part we have to determine the wasted work potential during this mixing process. So, in part B, so the exergy destroyed during a process can be determined from the exergy balance or directly from its definition, that is exergy destroyed is equal to T0 S gen, which is the entropy generated. So this entropy generated can be determined from the entropy balance. So entropy balance on the system and its immediate surrounding. So it gives S in dot minus S out dot plus entropy which is generated is equal to delta S dot of the system. So again this will be 0 because of the steady flow conditions. Now entropy in is M1 dot S1 plus M2 dot S2 minus, which is leaving, is M3 dot S3 minus, because of the heat which is going out, Q out dot, this is temperature of the surrounding, plus S dot gen, entropy generated is equal to 0. So from here we can get entropy generated is equal to M3 dot S3 minus M1 dot S1 minus M2 dot S2 plus Q dot out divided by T naught, which is the outside temperature. Now substituting all the values, and as exergy destroyed is equal to T naught S gen. So substituting the value of S gen from here, we can calculate X destroyed as T0 M3 dot S3 minus M2 dot S2 minus M1 dot S1 plus, so this is 298 Kelvin T naught minus M3 4.429 into S3, which is 1.0756 minus M2 0.429 into S2, which is 7.5081 minus M1 is 4 into S1 is 0.22447 plus Q dot out is 10 when it is converted into kilojoule per second divided by T naught, which is 298. So this comes out to be 202 kilowatt. So the total exergy destroyed, or the wasted work potential during this mixing process, is 202 kilowatt. So this ends this lecture, and we will see you in the next lecture. Thank you.